let's let C be a curve where C is the graph of a function y of x, where x is between a and b. And we want to find the length of C. In order to apply the length formula that we obtained earlier, we need to be able to parameterize the curve. To do so, observe that if x is between a and b, then the corresponding point on C has coordinates x comma f of x. So the points on the curve C has each point on the curve C has the form x comma f of x. So as x varies from a to b, we get x f of x traces all the points on C. So we define this vector function out of x to be the vector x comma f of x, and then clearly out of x parameterizes the curve C. So taking this parameterization for C, then we can apply the length formula we obtained earlier. So we can say the length of C is the integral from a to b of the square root of so here it'll be we take the derivative of the first component of the parameterization, and the derivative of x with respect to x is 1, and then it is square of that is still 1, and the derivative of the second component with respect to x would be f prime of x. We square that, we get f prime of x squared. So this is the integral that gives us the length of C. We can rewrite that as the integral from a to b of the square root of 1 plus dy dx squared. Okay, so let's apply this formula to find the length of the following curve. So let's say I have the curve C, which is the graph of the function y is equal to f of x, which is 1/6 x cubed plus half x to the negative 1. X is between 1 and 3. So what's the length? We know that the length would be the integral from 1 to 3, square root of 1 plus the derivative of f squared. So the derivative here would be, if you take the derivative, you get 163x squared, which would be 2x squared. Sorry, it'll be half x squared, and then here I get negative half times derivative of that would be negative x to the negative 2. So you get negative half x to the negative 2. So this is f prime of x here. So we square that. Now what we're going to show is that this integrand can be simplified to half x to the 2 plus x to the negative 2. And if we integrate this, then we get 14 divided by 3. So first, let's see how we simplify this to this integrand. So if I start with this integrand right here, actually let's start with the quantity inside of the root. So I get 1 plus half of x squared minus half of x to the negative 2 squared. And if I expand the square, then I get 1 plus 1/4 x to the 4, and then minus, we're going to get 2 times this times that. So if I get 2 times this, that's going to give me a half, and then the square of this guy would be 1/4 x to the negative 4th. So we get this quantity. 1 minus a half is a positive half, so we get positive half here. Now we're going to factor out 1/4 and x to the negative 4. So if I do that, the fact that I'm factoring out 1/4, then I have to multiply each term here by 4, and since I am factoring out x to the -4, I also have to multiply each one of them by x to the +4. So if I multiply this by 4, then this 1/4 goes away, and then if I multiply this by x to the 4, I get x to the 8. So that's what I have here. Half, if I multiply that by 4, I get a 2, and then if I multiply that by x to the 4, then I get 2x to the 4. If I multiply by 4, this 1/4 goes away. If I multiply by x to the 4, this goes away and gives me 1, so I get 1 here. So if I factor out 1/4 x to the -4, then I get x to the 8 plus 2x to the 4 plus 1. And this quantity here can be factored out, and because what we have here is x to the 4 squared plus 2 x to the 4 plus 1. So you can factor this out as x to the 4 plus 1 squared. So this is what we obtain, and then if I take the square root of that, what we're going to get is so if we take the square root of this, we're going to get the square root of this, which would be half x to the -2 times x to the 4 plus 1. So as a result, we get half x to the 2. So here, if I multiply out now, I get half x to the 2 plus half x to the -2. So this is what I get, half times x to the 2 plus x to the -2. So we see that the integrand can indeed be simplified to this, and now we integrate this. So the integral from 1 to 3 of half x squared plus x to the -2 dx is equal to, take the half out, we get integral from 1 to 3 of x squared plus x to the -2 dx, and then the antiderivative of x squared is x to the 3/3, and minus and the antiderivative of x to the -2 would be minus x to the -1, which is 1/x, and then plug in 3 and 1 and subtract. So if I plug in 3, we get 27/3 here, so that's 9, minus a third. If I plug in 1, I get 1/3 minus a 1, and then if I simplify that, I get 14/3. So we see that the length of this curve is 14 divided by 3. Okay, so just like the way here we have that the if I have a curve that is the graph of a function y of x from a to b, then the length of c is obtained by integrating from a to b the function root of 1 plus dy dx squared. Now, if I have a curve where it is the graph of a function x of y, so if x is equal to g of y, where y is between c and d, then the length of this curve would be the integral from c to d of the square root of 1 plus dx dy squared. So here you're taking the derivative of x with respect to y, or instead of writing dx dy, I could have written g prime of y squared. So as an example, if I have this curve where x is equal to y squared, y is between -1 and 1, this curve is the parabola that opens to the right from -1 to 1, so we get this piece, and we want to find the length of this curve. And according to the formula that we have just looked at, we take the length would be integral from -1 to 1, square root of 1 plus dx dy. So dx dy, derivative of x with respect to y would be 2y, and square that, so we get root of 1 plus 4y squared dy. and so that the length would be given by this integral, and then one can evaluate this integral to find the length. Okay, so I'm not going to show you how to evaluate this integral, but if you are given a curve in terms of a function of y, then we can use this length formula here. Okay, so this is it on arc lengths. In the next series of videos, we will start talking about curvature.